Everybody, welcome back to another fun and exciting geometry class. In today's lesson, we're going to be jumping into chapter number 6. This is on page 260 in your books. We're going to be proving polygons to be regular. Now, a lot of cool stuff that kind of goes along with this. You kind of got to get the concept down. Then we can start figuring out some really neat stuff that you can do with this. We're going to be actually doing mathematics in this chapter. I know sometimes geometry is like, this is not really a math class, and I get it, you don't do a ton of math in here. But in this chapter, we will be doing some math, and so maybe some of you are like, oh, finally I get to do some math. And you never thought you'd say that, but geometry has made you say that. So we will be doing that here in this chapter as well. So let's go ahead and look down here at the screen. You can look in your book as well. Let's talk about proving polygons to be regular. Now, regular polygons are both equal angular and equilateral. Okay, they have to fit both of those criteria, and I think we've talked about that before. So for something to be regular, it means that it's going to have equal angles and equal sides. So how will we prove that? Well, if we can prove that the sides are equal and we can prove that the angles are equal, then we've proved that it is a regular polygon. All right, easy enough, right? So let's go ahead and look at this. This is a six-sided shape. This is a hexagon. And so let's go ahead and look at this. We could, write whatever. Let's say that this is 7 inches. And so all of these have to be 7 inches, every single one of them. If one of them is not 7 inches, if this one's 6 inches, then the whole thing is messed up. Then this is not a regular polygon, okay? So that does not fit the criteria. What does that mean if one side is different? Well, that means that there's got to be some angles that are different as well, okay? So if one side is different, then some angles are also going to be different. It's kind of like a chain reaction right there. Or if the angles are different, then the side is different, depending on which way you're looking at it. So if this is 7 inches, then we have a regular shape. As soon as we know that they're all 7 inches, okay, if we know all the sides are the same, then we will know by default, because of that, we would know that, for example, these angles right here that connect these two sides, they have to be equal, okay, because all of the sides are equal. And you can go around the whole shape and do that. And I think we've already done that before. So we could say that's equal and that's equal. They're all equal to each other, okay. All right, there you can look down in your book at theorem number 76. An equilateral polygon inscribed in a circle is regular. So if we can take a polygon and we can put it inside of a circle, and if it touches all of the spots, so like if all of these spots, all of these angles right here, if they touch the circle, if it's inscribed, what does inscribed mean? It means that it's touching on all of its vertices. So if every vertex in this 5-sided shape, this pentagon, if it's touching the circle in every location, then we know that it's going to be regular. So if we can put this in here, and if indeed it does touch in all of these spots, and I'm not going to be able to get it perfect, although it's pretty close, we're going to call that, because it's touching, look, it's touching here, we could go around this thing and we could label these. So we could say, okay, this is angle A, angle B, C, D, and E. And let's talk about this for just a second before we move on. So what are these points? Well, these are vertices, right? This is the vertex of this angle that's coming together. So each one of these is going to be a vertices in your shape. What is it on the circle? So it's a vertex on the shape, on the polygon. What is it on the circle? Because it's different. You call it something different. You would not call this a vertex on the circle. All right, so you just call this a point on the circle. But look what we formed right here with like AE. AE forms what? What is that called? It forms a chord, right? And AB forms a chord. And BC forms a chord. DC forms a chord. And DE forms a chord. Now look, they don't just form chords, they also form equal chords. Why are all of those equal? Okay, they're all equal because these points, E is an equal distance to A, is an equal distance to B. In other words, their arcs are all the same as well, right? So they're all going to be equal. So there's lots of stuff going on here. Like I said, we can do some cool things with this because it does create so many different things that are true. Also, obviously all these angles are the same. We just talked about that. All the sides are the same. The chords are the same. We're going to get into here in just a little bit. We're going to get into like when you add a central point and you add central angles to this, okay, that all of these central angles are going to be equal, okay? And all kinds of different stuff can come out of this. It gets really, not complicated is not the right word, but it's like this web, right? As you work your way around the shape and the circle. So an equilateral polygon inscribed in a circle is regular. If you can get those vertices to touch the circle in all 5 points, if it's a pentagon, all 5 points have to touch the circle, then because of that, it's equilateral, and then you would also know that it's equiangular or it is regular. All right. Theorem 76, this is on the bottom of page 260. If a circle is divided into any number of equal parts, there are some things that are true. And we kind of talked about it when we went over here. So if we take the circle and we divide it in equal parts, the chords joining the successive points of the division form a regular polygon that is inscribed in the given circle. So if we take our circle and we just form our points and we make them equal to each other. So let's do this. Let's do a point here, a point here, a point here. This should look somewhat familiar to you, right? So this is like if it's a clock, then it's 12, 3, 6, and 9. All right. So basically we're taking that circle and we're dividing it into quarters. So what happens if we join our vertices here? So if we take our vertex here and we join it to this one, we join it to this one, we join it to this one, and we join it to this one. Well, we've created a square in our circle. Okay, so that would mean that this side is equal to this side, is equal to this side, is equal to this side. Okay. And then, there's, again, just some cool things that just keep coming off of this thing. All right, the next one, letter B, the tangents drawn at the points of division form a regular polygon circumscribed about the given circle. What does that mean? Well, let's take now, instead of drawing chords, we're going to draw tangents. And these ones are a little bit harder to draw. And there's going to be, they get a little weird trying to draw them on this program just because they don't end up coming out perfect. But we're going to draw tangents. It's not going to be perfect. And here we go, this last one right there. I don't know, that's close enough. All right. So as you can see, I kind of drew them extra, right? They went outside of the range and they, I have some overlap here. But look what's formed. We formed what? Outside of the circle. We formed a square outside of the circle. So we have a square inside the circle. It's kind of more like a diamond, right? So we have a square or a diamond inside the circle, and then outside the circle we also have a square. And we could do this with as many points as we wanted to, as long as they're equal distant. Okay, so we put 4 points on and we got a square. What if we put 5 points on? If we put 5 points that are equal distant, we would get a regular pentagon. What if we did it with 6 points, 7 points, 8 points? We'd get an octagon. See, it's just however many points you put, that's what shape you get, because that's how many sides that you're going to end up having. And you would get the same one inside as you got outside. They would just look a little different because they're shifted. Like this square is shifted, basically standing on edge. You would do the same thing with the other shapes just because of the way that the lines fall in there. But the point is that you would get, if you put these points equidistant around your circle, you will get a shape based on however many points that you put onto your circle. All right, next is on page number 261. Corollary 77.1. If the midpoints of the arcs subtended by the sides of a regular inscribed polygon are joined to the adjacent vertices, then the regular inscribed polygon of double the sides is formed. All right, check this out. So here's what they're saying. I know that's a lot of jargon right there. It's a lot of mumbo jumbo, right? Kind of hard to figure out what they're saying. If we Okay, so here's a point. Let's go ahead and mark our vertices, right? So here's our vertices for this shape. It's a square. There's 4 of them. What if we put one in the middle of all of these? So that's what they're saying right there. What if we do this? Let's go back up and read what it says. If midpoint of the arcs, so here's the arc. What did I do? I put a midpoint right there, right? Okay. So if I put a midpoint on the arc, what happens? It's got to be regular, okay? So it does have to be a regular polygon. Then the regular inscribed polygon of double the sides is formed. And this one won't be as pretty as the original one because I'm just going to freehand draw these lines in here, okay? But look what happens. All right, so now what do we have? We have our square, original square, and then we have this new shape that's formed by these light blue lines. How many sides does that shape have? Okay, that shape has 8 sides. It has double the amount of sides. We could count them, so it's 1, 2, 3, 4, 5, 6, 7, and 8 sides. Now, here's the cool thing. We could do it again if we wanted to. Now, it would get a little weird on us, but we could take this. My program is not going to really allow you to see it very well. Okay, but I could blow that up and you could see where it's actually, we're actually doing the same thing again. Now, how many sides is that going to have? Okay, well, if we had 4 sides and went to 8 sides, then this new shape, this new yellow shape that I'm forming is going to have how many sides? It's going to have 16 sides. So you could keep going. Keep going, keep going, and keep going. Notice something. This is kind of cool. Notice something that as I keep going, notice that my lines get shorter and they get closer to the arc of the circle. Okay? So what's happening is, yes, my lines are straight, but they're starting to look more and more like a circle. The more lines I put on there, the more it looks like a circle. What if I put another point here in the middle and did it again with this green line? Well, it's getting even closer to the shape of the circle. Now, check out this next corollary, and then I'm going to make a cool point, and you're going to be like, wow, maybe mind blown. All right, so watch out. Don't want to blow your mind. Don't want to hurt you. But the corollary 77.2 says if tangents are drawn at the midpoints of the arcs of the adjacent points of tangency of the sides of the regular polygon that is circumscribed, then a regular circumscribed polygon of double the number of sides is formed. Again, lots of jargon, but what does it mean? Well, here's what it means. If we do the same thing here, if we take a point and we draw a line of tangency out here, what we're doing is we are creating, again, we're creating another shape out here. And now look at this shape this time, right? Okay, so it's very similar, but it's starting to follow the shape of the circle again. So if we keep doing that and we keep putting our point here and we keep putting a tangent right here, it's going to keep making this thing very close to the shape of the circle. And we can keep doing that and keep doing that over and over until basically the lines are really close to the shape of the circle. Now, here's the point that I wanted to make. When we do that with our shape, so let's go back to this one right here. And I'm just going to put some lines in here so you can kind of see what I'm talking about. So if I do this again right here, right? Again, that's getting very close to the shape of the circle. So if I do that again, now these are getting very close to the curve of the circle. The line never curves, but it's getting closer and closer. Now, what if I do that with these lines out here? So again, I do a tangent, and then I do another tangent. Now, if you'll look, if we zoom this way in, look at these lines right here, and I'll kind of make them with the white. So this line, and then this green line. Okay, or no, excuse me, this blue line. Okay. Now, if you'll see that, there's only this little bit, this little piece right here, if you will, that's like not part of the circle line. If you wonder how mathematicians figured out what is the curvature of the circle, so here we have our circle curving, right? Okay. So if they wanted to figure out what's the curvature of the circle, here's what they did. They use what's called limits, and they use the circle as the limit. And then they kept drawing these lines on the inside and the outside, and they kept measuring the straight lines, because you can measure straight lines. You can't measure the arc of the circle, but you can measure the straight lines. So they measured the straight lines on the inside of the shape, and then they measured the lines on the outside of the shape, and they used limits to help them understand what, check this out, what pi equals. Okay, and so for so long you've been like, what is pi? I know pi is 3.14, blah, blah, blah. But what is pi exactly? Pi is the curvature of the circle, right? It's how it curves in there. Well, the way that they figured out what pi equals, see, they figured out pi way before that they had, computers and all these other things, calculators. So they had to figure out pi by hand. How did they do that? By figuring out the perimeter of these shapes. As they figured out the perimeter of the inside shape and figured out the perimeter of the outside shape, it allowed them to calculate pretty close what pi actually equals. So that's pretty cool. All right, maybe you're like, oh, you built that up and then it was nothing. Yeah, I know, I'm sorry. So, but I like it. I think it's pretty cool. It's just amazing what people were able to do before the invent of computers with mathematics, and they were way ahead of us. They just were. And we rely on computers and calculators a lot, where they relied on their mind to be able to figure things out. So, all right, hopefully you learned something there. If you missed anything, you can always slide it back, watch it again. That's all I've got for you in this lesson. Have a good one. We'll see you later.